and last talk of the afternoon. Our speaker is Martin Lohmann from the University of British Columbia, Vancouver, and he will talk about the critical behavior of 544.
Thank you. Thank you also to the organizers for giving me the opportunity. So this is another talk about the 5-4 model. You might have noticed that it's maybe its phenomenology is not quite as attractive as other models that you've heard about, but it is still a non-trivial, and in fact many of the techniques of our community have been first developed on that model. So, but I will not give a technical talk. It's more supposed to be a talk, sort of like an overview directed at those people that might at some point want to learn the techniques. So the 544 model is used to model phase transitions, and for those of you who don't know what a phase transition is, it is when order appears in a system of many particles, as for example the temperature decreases. There might be some phase transitions that we will never understand, for example why water molecules order into crystals if the temperature decreases, but there's other phase transitions which there's a little bit known about, and especially about magnetic systems. So you see a lot of order in the picture here, but I'm not actually interested in the order that you can see with your bare eyes. Rather, the question is, so you have a lot of little grains of iron here in this picture, and the question is, why do they align with the magnetic field that is emitted from the big magnet in the middle? So the magnetic field emitted by that magnet is not actually very strong. So the iron atoms in each of these grains, they interact with the magnetic field, but the magnetic field is very weak as opposed to the other forces that act on it. So the question is, why do they cooperate or order in some way so that they would align with the magnetic field? And in fact, that's not always the case. If you heat up this picture, then at some point the degree of cooperation between the iron atoms just breaks down. So at very cold temperatures there's sort of perfect cooperation, and then as you reach a certain critical temperature, which is called the Curie temperature, then they will not cooperate anymore and they will not align with the magnetic field anymore. And that is kind of the phase transition. So losing this kind of order as you heat up magnets or iron or some metal is what I'm concerned about. Now there is some models you could write down for how these atoms interact with each other. But maybe I first want to talk about the microscopic models. So you could think about these atoms to be sitting at a certain location, and then they have a certain magnetic moment. And if your temperature is small and you apply a weak magnetic field, H, then all these magnetic moments will align in a certain way. And if you take the average magnetic moment of, average over certain of these atoms, then you will see that they will align with the magnetic field, but the degree of alignment will not really depend on the magnitude. It will only depend on the direction of the magnetic field. So the magnetization will be a function of the external magnetic field divided by its length. While if your temperature was higher than that critical temperature, you would not see any, there will probably be a little bit more likely to point into the direction of the magnetic field, but not very much. And in this talk, I'll be actually interested in what happens exactly at this temperature. So how do these pictures look like exactly at the critical temperature? So how does one model magnets? It depends on how much quantum mechanics you want to use. I don't want to use any quantum mechanics. And if you don't use any quantum mechanics, you could say that a dipole, so a single atom for me, just has a magnetic moment of a certain strength, which I call R, and a direction. So this is a vector with that length. And then to first order, the interaction of this dipole with the magnetic field is just linear in both. So this is the external magnetic field H, and you decrease the potential energy of a dipole if you align with the magnetic field. That's this term with a minus sign. And then also the dipoles interact with each other, and in the same way, kind of in a bilinear way in the direction of the dipoles. So this is sort of a bilinear form in the two of them. You could ask yourself, how many dipoles does each dipole see? And the simplest case is when a dipole at x only sees a dipole, like interacts with a dipole at y if it's a neighbor of that in the lattice. So all my atoms sit on a lattice, which I just choose to be a cubic one. You could choose whatever you want. And then statistical mechanics tells us that dipole configurations are distributed according to a probability measure like this. There's a product measure over just the Cartesian measure on the sphere here, and then there's this Gibbs factor, which is e to the minus the inverse temperature times the potential energy. Okay, and this constant z here just normalizes the measure, so it's the integral of the Gibbs factor. And then statistical mechanics also tells you how you compute observables from this measure. So there's two I will focus on. One is the magnetic susceptibility, and that's just the sum of the spin-spin correlations at zero external magnetic field. So I put this H here equal to 0, and I sum all the spin-spin correlations. And the other one I want to discuss is the magnetization, and that's the sum of all expectation values, the average of all the expectation values of the spins in non-zero magnetic field. So here I still have my H. You could write both of them as derivatives with respect to the external fields of this normalization factor here if you want to. Okay, so this model has been analyzed. It's actually not too difficult to analyze as a perturbation of this product measure here if you have a very high temperature, much larger than this critical temperature. It has also been investigated for very small temperatures. There's an important work by Fröhlich, Simon, and Spencer, and a very hard work by Balaban. But exactly at the critical temperature, this model is out of reach. And from my perspective, there's two technical problems there. The first is that this constraint here is so strong. So the constraint that you have to exactly lie on a sphere. Something that's much easier to work with is if you replace this delta function by a function which is just peaked around the sphere, and I want to change. I want to use exactly this kind of function. So you see, it's an exponential of e to the minus beta times something that. So this is 0 if your spin has exactly length r, and that it suppresses spins which don't exactly have that length. But maybe the more important problem about this model at criticality is that right now the physical dimension is the most important problem. So the 3 dimensions. These are this is a very complicated dimension at criticality. 1 and 2 dimensions would be somehow easier in the sense that there are some special tools that might not be very easy themselves, but they just work and are sort of robust. And certainly dimensions bigger than 4, there's very robust tools, but 3 dimensions is not really applicable. I mean, we don't really know what to do with it at criticality. And I want to talk about 4 dimensions instead, which is sort of the upper critical case. Okay? So these are the 2 simplifications I will do to that model here, to that the model defined by this energy. And so first I changed to 4 dimensions, and then instead of having a product measure over measures on the sphere, I just have the standard Euclidean measure, and I have this extra factor here that forces my spins to be close to these have length about r. Now there's a common way to scale this, so you can just scale it, and so there was this spin-spin interaction in here, and you want to scale your variable so that this has coefficients of order 1. And then then if you do the scaling, so you scale all fields by 1 over square root of beta, then the model actually looks like this. So I have spin-spin correlations, spin-spin interactions now that have just a 1/2 in front of it instead of a beta over 2. And then you multiply out this quartic function that restricts your spins to have length around r, and then you get a quartic polynomial like this. And so the coefficient of the quartic part is something like the temperature, and the coefficient of the quadratic part is something like the length of the dipole, so the dipole moment, if you want. I guess I've also rescaled the magnetic field. I didn't really show that. And then another small modification I want. So we're now here in 4 dimensions. Doesn't really make any particular sense to choose my spins to have 3 components. So I will just have them have n components, and that's the phi to the 4 theory. So it's just a scaling of this simple magnetic model, but in 4 dimensions, and with spins that don't have to have fixed length. Okay. And so, just like the original model had this phase transition and temperature, this also will have some kind of phase transition, and it's easier to sort of parameterize the parameter you vary to make that have that be nu. And so here in this case, if you just fix lambda, there will be a critical value of nu for this model where there's some kind of critical behavior or a phase transition. And more precisely, what is the behavior at this phase transition for the 2 observables that I wrote down before? So this the chi, the susceptibility, is the sum of the spin-spin correlations. That will diverge as you approach the critical point. If you want, you can take that to be the definition of what a critical point is. And if you approach it from above in the nu plane, then it's supposed to diverge exactly in this way. So it blows up like the distance between the nu and the critical nu, but there's some log corrections to it, which depend on the number of spins. And then the magnetization, how does that behave? If you put it directly at the critical point, and now you turn off your magnetic field, then the magnetization should vanish like h to the 1/3 with log corrections. So I said if you're below the critical temperature, this should not vanish as h goes to 0. If you're above the critical temperature, it vanishes linearly, and at the critical temperature, it should vanish like h to the 1/3 with log corrections. So notice that we are concerned here with, in this limit, we are concerned with the high temperature phase. Nu bigger than nu critical corresponds to high temperature. And I will just refer to these logarithms here as logarithmic corrections to mean field scaling. There's a sort of a simple calculation you can do to see where the h to the 1/3 and that thing is coming from. And but you cannot see the log corrections in any easy way. In fact, the method that one uses to see these log corrections is the renormalization group. And what that renormalization group claims is that the correlations of this model actually look like the correlations in a Gaussian free field theory, with a mass that depends on the distance to the critical point, but not just linear like here, but there's log corrections in this mass dependence, and that's where these logarithms are here coming from. And the fact that your correlations decay to Gaussian ones is something that you call asymptotic freedom. I want to give the main idea of the main mechanism of the renormalization group. And that's easiest to see in sort of multi-scale perturbation theory. So I just want to mention quickly how that story goes. And I will show how multi-scale perturbation theory works for the susceptibility. So that's, again, it's the sum of the spin-spin correlations. And so if the prediction of the renormalization group is correct, that these correlations will look like the ones of a Gaussian free field, then maybe we just try to see where there's a Gaussian free field in here. And so this is the quadratic form of a Gaussian free field that is massless. And so maybe I just extract, like I separate this term from the other terms here. I will expect it to have some mass, so maybe I try to take this. These are mass terms, so I will try to take some mass out of here. And then, so I separate off this quadratic form, and what I'm left with is just some perturbation of that. And so I want to study this object formally as a perturbation of this Gaussian measure, the free field measure. And what does mean to use to study this as a perturbation? Well, I just expand the exponential like that, and then I illegally commute the series with all the other limits like that. Now it might be very hard to justify why one can do that, but once you have done it, you can just calculate all the numbers here. And so why can you do that? Well, this is a Gaussian measure, and this is just the power of a polynomial, and there's some other polynomial. So there's a rule that tells you how to compute these integrals, which is called the Wick rule. And what it tells you to do is, if you want to have the value of that, you just single out pairs of fields, for example, these two, or you can pair this with something in here, and then you delete the pairs and you replace them by the entry of the inverse matrix of the covariance, if you want, of the Gaussian field. And you do that until you have no fields left, and then you just get a number, and that is the number of that's the value of the integral if you do that for all ways of pairing. And so let's do that for two important terms in this particular sum. The first term is the one where you just have k equal to 0 here, so this guy disappears. There's only two fields that you can pair, and so the big theorem tells you that the value of this integral now is just the covariance matrix at 0 and x, and I'm supposed to sum that over all x and take the thermodynamic limit. So I just get the sum over the inverse elements of the Laplacian on Z4 plus a mass squared, and you can convince yourself that this is a computation you can do exactly because of translation invariance if you want, and then you get m to the minus 2 for that. So for a Gaussian free field, the susceptibility is just the inverse of the mass squared, okay? It's just basically what I want to drive home. Now what about other important terms? There's one when you have k equal to 2 here, which is important. So if you have k equal to 2, you have to take the square of this guy and insert it in here. There will be one cross term where you cross a new prime with a lambda, and then what you could do is you could contract that field here with 1 in here, that field with 1 in here, and then the remaining two that haven't been contracted with these two. And what that will give you, so the contractions of these two fields gives you an m to the minus 4, just by this kind of calculation, and the contraction of the remaining two fields here with these two gives you the sum of the squares of the covariance, okay? And now how to compute this number here? Well, I guess there might be some exact formulas, but in principle you you can't really evaluate this as simply as that, and you might just want to get an estimate for it. And the easiest way to estimate it is to say, okay, I know how to sum over one factor of covariance, so the other one I just take outside and take the supremum over it. I guess these are positive numbers, so that's going to be a bound. And then so the supremum is obtained at x prime equal to 0, so and it's just a constant in 4 dimensions, so you get a constant times m to the minus 2 as a sort of a simple bound, okay? But that's not actually very accurate. And what multiscale perturbation theory does, it gives you accurate bounds on these kind of objects without any additional trick. Like you still just replace sort of squares by a supremum and a sum. And how do you do that? So how do I get a better estimate on this thing without using anything more? Well, you will have to use that the Green's function can actually be written as a sum over scales. And so there's one scale. There's a sort of a unit scale, then there's a scale L, which is just an arbitrary chosen scale, the scale L squared, L cubed, and so on, all the way up to M inverse. M inverse is the highest scale that you will use. And the contribution to your covariance from scale J is small in absolute value, as like L to the minus 2J, but it has a long range, so it depends on this point X here only very weakly, like L to the minus Jx. So these functions f you can think of them as just one function that is more or less independent of J, and it's quickly decaying, but since I'm not inserting X itself, but the scaled version of it, sort of decays very slowly, like on length scales L to the J. Now if I insert this into my computation of the sum of the Green's function squares, so I just insert this identity, then I get that. And now I promised you I will only use a supremum on L1 bounds, so I have to take one of these guys out of the sum and replace it by its supremum. But the idea of multiscale theory is to take the one out that has the slower decay. So you keep the one inside the sum that has the fast decay. So let's say the one that decays fast is J prime. So J prime is the smaller scale. Then I leave that inside the sum. And this is just, well, as I said, it's just a Schwarz function. So this will have some finite supremum. So this comes out as a constant. My sum now is over scales J, which are bigger than J prime, right? And the rest has not changed. So now this might be, depending on how you do the decomposition, you can just evaluate this exactly, just like before. Sometimes you can't, but clearly this is just a Riemann sum approximation to some integral, but it's missing the volume factor. And the volume factor would be L to the minus J for J prime. And so I just change my minus 2J prime to plus 2J prime, and then I insert the volume factor. I get the integral of that Schwarz function, which is another constant, and so I get this kind of bound. And now what does this bound look like? Well, it is a sum over scale differences. So if you first sum over a base scale j prime, and then over scales bigger than that times an exponentially decaying factor in the scale difference. So the sum over j, if you do the sum over j first, that's just going to give you a number which is bounded and more or less independent of what j prime is. But then you have to sum over j prime, and there's log m inverse many of them, and so you get that this is actually bounded by log m inverse instead of m to the minus 2 as the original bound told you. And this is actually this is good asymptotics. So the main idea in multi-scale perturbation theory is you're still allowed to use these L1, L infinity kind of bounds, but you should always keep the lower scale for the L1. Okay, and that will reorganize all your bounds so that you get the accurate behavior of the object you're bounding. Okay, and actually this log is exactly the source of all the logs in the previous slides, if you unravel stuff. Now, how do you get these multi-scale decompositions of the propagator? Well, I will show you one method of doing it. That method is it's actually sort of so useful by itself that we will never actually just use it for that purpose, but you could use it for that purpose, and that's called a block spin transformation. So this is the covariance G that you might want to decompose, and it defines some kind of Gaussian measure, and that we are interested in perturbations of this Gaussian measure. For example, you could put a source term here, and if you put a source term here, then you will just basically compute the covariance, and then you could read off the decomposition from that. But let's just look at this perturbation of the Gaussian measure with covariance G, and my spin configuration. I want to block my to sort my spins into groups, and each group will have a certain size, which it's L to the D. So I will group them into blocks like that. Every block has a side length L, which is going to be my scale parameter, and the blocks are centered at points in a causal lattice, which are the red points here, and the cos lattice I will call lambda L. And then in this integral, I want to condition on what is the average of the spins on a block. Okay, that is so I insert a unity here, and that unity is an integral over a delta function which restricts the average of over a block of the original integration field to be equal to a certain value. And now the trick is, so this is just inserting an identity, and now the trick is to commute the integrations here. And then if you do that, you can translate the original integration field to get rid of this delta function. The easiest way to think about the delta function is actually that it's sort of e to the minus infinity times that stuff squared. So it's something like a Gaussian measure, like a delta function. And then you have a Gaussian here, you have a Gaussian here. So two quadratic forms, and you just go to the minimizer of that. And you can work that out explicitly. So you get that this integral is just the same as this integral. And the second integral has now a covariance, instead of having the covariance G, it now has a covariance G0, which could be the first element of your multi-scale decomposition. And it's sort of an infrared regularized version of your initial propagator. And then you also generate a Gaussian measure for the block spin field G prime, and the block spin field enters the perturbation of your measure. In this way, you would call this a background field. Okay. And so if you insert, for example, for W a linear expression in the fields, then you can read from this. You can read off the first term of your multi-scale decomposition of the propagator if you wanted to. But really, this formula is very general, and I will just work. I will work only with this formula. I will not do any perturbation theory, and it tells you that it is sort of a prescription of mapping one perturbation to another perturbation, which is the integral over phi 0 of that guy, and you can iterate that. And then if you iterate this procedure by blocking into bigger and bigger blocks, you get these maps that sort of integrate out the fields at a certain length scale, and that's what I call the RG map. And so the background fields are just sort of they're constructed by repeatedly inserting the previous background into the previous background field constructions, and the propagators of the covariances of the fluctuation are also just repeatedly constructed from this formula. Now, maybe a remark is that I always write all these effective interactions, like I will call these effective interactions. I always write them as exponentials of something, but this is just notation. So for me, exponential of something, this is just one object here, okay? And this object is defined in terms of the previous e to the minus wj, if this e to the minus wj is integrable with respect to that Gaussian measure, which is just a condition on the determinants. And since I'm only, like, this transformation just consists of inserting identities, what emerges is that you can compute your original partition function in terms of any of these effective interactions. So you can just choose you can choose to iterate this transformation as long as you want. You can always compute the original partition function by integrating out the remaining scales in one step. And that's sort of the remaining propagator here. And the way that this object differs from the original definition of the partition function is that it's an integral over much fewer degrees of freedom. So originally you had to integrate over this bold L to the 4 degrees of freedom, and now, for example, if I could reach an n so that this thing here is just 1, then I would only have a one-dimensional integral. And it's much simpler to analyze if you can get some information about what these effective actions are. Okay, so what about this RG map, this RG transformation? What does it do if I start applying it to the original problem I had, which was defined in terms of these quartic local interactions? Well, if you apply it to one quartic local interaction, you will not get anything out that looks of the same form as before. There's two problems. First of all, so quartic local. So local means that you have this perfect factorization of that your e to the minus v is a product over x of e to the minus v is just at a single spin. But now I diagonalize my covariance here. Now every factor for a given x here depends actually on all the integration fields, phi y prime, I suppose, that I have distance about L to the j from it, and so they will all be coupled together. So the factorization is not preserved. There's some models where it is preserved, but it's not the ones I'm going to discuss here. And the other problem is that so this is not going to be quartic anymore in the fields, because it's a convolution of a Gaussian with something, so it can decay at most quadratically. And it's sort of like the behavior at large fields of this kind of object is not. It's not clear how to deal with it. And the methods that have been developed to deal with these two problems. So first, about the factorization problem. There you can find a representation of these effective actions which have partial factorization. These are called polymer gas representations, and they involve objects that are called activities. And so these functions, they depend on. So they're parameterized by subsets of your lattice, and the interpretation of them is that fields inside each of these subsets are coupled together, but your activities do not depend on fields that are outside of these sets. Maybe I don't go into exactly what this representation means, but I want to mention is that it looks abstract, but there's a very well-defined way of how to compute something like this susceptibility or something from these representations. These are called Maya expansions. If you can get some kind of bounds on these objects, then you can compute all the thermodynamic quantities from them. So this is sort of the technical tool to control the loss of locality. What about the more detailed structure of these activities? Particularly, how do they depend at large fields? So there's many different ways of doing this. This is the way that Garetsky-Kupiainen did it, or sort of a variant of that. That's easier to put on a slide. These activities are sort of two first-order local exponentials. of a quartic polynomial. This is just a quartic polynomial. So the linear and quadratic and the constant parts of these polynomials are sort of present for every point in your set, but the non-Gaussian, or like the cubic and quartic parts, are not always there. They're just you can always only have them for points in a set where your field is small enough. And so this set d of psi depends on your particular field that you insert into the activity, and it's the points. So d of psi are the points where psi is large, and the complement is where it's small in a certain sense. And your activity should always include the large field set. It should be sort of deep contained inside of them. And then there's more information, which is first of all the corrections to this first order approximation if the field is small. That is encoded in these functions if the large field set is just the empty set. And there are some conditions that this function satisfies if D is the empty set. So it should be something like what people call RG irrelevant. Okay, and then there's also information stored in this about how this function behaves at large fields. So this kind of decay is not true at large fields because it just has this quartic term in front of it. And instead, there are some conditions about how this decays if the large field set intersects X. Okay. So this is sort of like, this is where the stuff becomes technical, but you just have to believe that you can write down the RG map, which was pretty explicit on the last slide, in terms of these coordinates. So in terms of these constants that parameterize the polynomial, and these the sort of large field activities, if you want to call them that. And the formula for that is nothing you could write down on a slide easily, but it is explicit, and then you can try to work with it. Okay. Now, I want to show some graphics now about how the RG map acts. What is the flow of these coordinates under the RG map? And I first want to talk about the symmetric case, which is where you don't have magnetic fields, and all the functions I showed previously are invariant under psi to minus psi, or I guess under rotations of the vector psi. And in the symmetric case, there's these explicit RG trajectories, so that you can insert into your RG map at the first scale some mass and zero coupling so zero lambda, non-zero or non-negative initial nu. And then this symbol here is more or less the zero for activities. There's some kind of exponential which is defined on activities, and if you exponentiate that, you just get 1. So that's why it's 0 for activities. And then you can start applying your RG map to the interaction which is parameterized by these things, and you get explicit formulas. They're not as short as you would hope, but you can write them down explicitly. And then you could ask yourself if you can do perturbation theory around these trivial trajectories. And the first thing you ask yourself if you want to perturb around a dynamical system is does the derivative of the map that defines the system look like on these trajectories? So that's linear stability. So you compute the derivative with respect to these coordinates, and you will see that unfortunately derivative has eigenvalues which are not all its eigenvalues are less than 1, which would be linear stability for dynamical systems. So the derivatives with respect to g, whatever that means, they all have eigenvalues less than 1. So the order of the inverse of the scale parameter, but the derivative with respect to the lambda coefficient is exactly 1, and the one with respect to the nu coefficient is bigger than 1. And so these trajectories are not linearly stable. But what you could still hope is that maybe you can do some kind of perturbation theory around stable, around invariant surfaces around these trajectories. So the plot here is supposed to be the one where mu0 is equal to 0. In this case, actually, the trajectory just doesn't move at all. So this is just a fixed point that's supposed to be at this point. And then if you're starting with initial values that are exactly on this. So this is the g direction. This is the sort of lambda direction. This is the g direction, and then the vertical direction is the nu direction. If you start at a point that is exactly on the surface, it will flow pretty fast to the middle here. So the g will contract to become this zero here. There's a sort of activity kind of zero, and then the lambda will flow also to zero. But if you start a little bit above the surface, then you will just be driven away from the surface. Okay. So you would ask yourself if you can construct an invariant surface of that kind for this dynamical system, and that was done in the case. So in the case of the perturbations of the fixed point by Gavetsky-Kopianin in '85 and by Feldman-Mannion-Rivas-Saussignon in '87, independently of that, that I construct part of that picture I just showed you. So what exactly do they do? They fix a number n, which is going to be the maximum number of iterations of your RG map, and then they prove that if you they construct a set of initial conditions so that you can iterate your RG map n times on these initial conditions. So like I only show these two parameters now. I don't show this activity g anymore. Say you start with a given lambda, which is not necessary, so it's going to be positive, and that's just this vertical line here. Then they show that there's an interval of news, so that if you start anywhere, so with that particular lambda and in this interval of news, you can iterate, say, 4 times. That's these blue lines are sort of the extreme case. And then if you start a little bit inside this interval, so lambda is still the same, but nu is now a little bit more restricted, then you can maybe iterate it 10 times, or you could, if you start even closer to, well, if you start even further inside the interval, you can iterate it 50 times and so on. And clearly, if you just intersect all these intervals, what you will end up is on a line, or if you have the other coordinate on a surface, and that is the invariant surface. So the intersection of these initial conditions that they construct is the part of this invariant surface that I showed you on the previous slide. And what happens if you're on the surface that you're always, the RG map can be applied infinitely often to you, and you will end up in this RG fixed point 0, 0, 0. And so all these lines sort of, if you start on this black line, then you will just end up in here after infinitely many iterations. And given some lambda 0, and like you start at 0 for the activities, the value, so that so this is this value here, that you are on the critical surface is exactly the critical chemical potential in the original model. So the original 544 model, I promised you, has a critical temperature, critical nu, and that is the nu is exactly this one that they construct. And they show also that the model started with these parameters flows to the Gaussian, the massless Gaussian free field. So the lambda goes to 0. It goes to 0 actually like 1 over the number of iterations. So after n iterations, your lambda is 1 over n about, and the nu after n iterations is sort of also 1 over n, or minus 1 over n. And correlations will decay like the ones of the massless free field at large distances. That's what they prove. So this is a sort of perturbation theory for the fixed point of the RG map. What about these other Gaussian trajectories? Well, perturbations of these were constructed by Hara and Tasaki in '87. And what do they do? So they start not right on the critical manifold, which is parameterized by this number, but a little bit above it. So they add a nu 0 prime, which is positive. And then, so if you start quite a bit above it, then you will stay close to the critical flow for a certain while, but at some point you will diverge away from it. And so what happens to your coupling constant is that it will decrease, but at some point it will sort of not decrease very much anymore. It will just stabilize at this value, which is the vertical line here. But the value of nu will exponentially diverge. And if you start closer to the critical manifold, then you will stay closer to the critical trajectory for longer, but at some point you will again diverge away from it. And so how do they construct these curves? They for a certain number of iterations of the RG map, they compare to the critical flow, and how many do you have to take? So it just depends on how close you start to the critical surface. This is the formula for it. And then, but then after at some point you just are too far away from the critical surface, and then you will have to start comparing to these to the massive Gaussian trajectories. And so that happens after that scale. But which massive Gaussian trajectory should you take to compare to? Well, the mass of it is a function of the distance, your original distance to the critical manifold. And this function is not just the mass, is not just the distance itself, but it has this log correction. So it's only if you choose it exactly like this that you will be able to perturb around the massive trajectory at large scales. And yeah, you can actually see these exponents coming up from explicit calculations like the perturbative ones I did before. And as I mentioned also before, is that for Gaussian correlations, the susceptibility is just sort of the inverse of the mass. And so the same is here the case. The correlations will be asymptotically just, well, they will be close to the Gaussian ones anyway, and with this mass, and so the susceptibility will blow up just like this with the log corrections. Okay. Well, maybe I should mention that this was really proven only in the single component case by Hara and Tasaki, and the multi-component case follows. The proof is sort of similar to that, but it was just worked out only recently. And there's an interesting application to a probabilistic model, the weakly self-avoiding Borg, that can be also treated like this. And, okay. So this is all the story for the symmetric perturbations of these explicit trajectories. What about the non-symmetric ones where you have magnetization? Well, you again have exactly solvable or like explicit trajectories that start at a non-zero magnetic field, non-negative initial nu, and all the other coupling constants are 0. And so maybe you could do perturbation theory around them. Well, what about linear stability? You have just more eigenvalues that are positive. So before we only had this L squared, which are bigger than 1. You only had the L squared before. Now you have 2 more corresponding to H and to kappa, just the cubic coupling constant. But these don't, like these coupling constants, they don't really have the interpretation of something you should fix to be on an invariant manifold. So it's not really clear if you could construct perturbations, but I think it's probably possible to construct sort of generic perturbations of these trajectories. You just have to you have to change your block spin procedure a little bit. So at every step you should do certain. So there was this minimization problem that happened when I computed the integrals in the block spin transformation, and there you should sort of include the magnetic field into that, and that would remove your linear coupling constant. So this eigenvalue is not a problem anymore. And this one, the kappa one, doesn't scale up very fast, so you'll probably still make it to compare with these explicit trajectories at some point. Yeah?
Earlier when you did this block spin procedure, when you had the fluctuation field, I missed, is it a spatially averaging to 0, the fluctuation field?
What do you mean spatially averaging? No, it's
for every sample when you look at the.
Yeah, if you fix your block field, it should be exactly equal to the average. Should be exactly equal to the block spin. So there's some sort of the formulas there's some sort of rank 1 stuff in there. So they're not really Gaussian measures the way I wrote them, I suppose. Well, maybe they are like even. Yeah, I don't know if I'm answering your question. Okay, but what was I at? I was sort of like you want to do the same kind of construction that Hara did for these trajectories. So you start a little bit away from the trajectories, and you want to at some point compare again to them. And I guess you could do it, but you will have to sort of manipulate the algebra at some very basic level. And so these arguments are always so technical that it's not something that anybody wants to do. And that's why this has never been done. But there's a simpler argument if you just the only perturbation you're interested in is really the one where you turn on the magnetic field, and that is because multiplying So like turning on magnetic fields for the original spins is kind of the same as turning it on for the block spins. There's an explicit formula of that kind. If you apply the RG transformation to something which is just symmetric plus a magnetic field, you might as well just apply it only to the symmetric part and multiply with the magnetic field later. If you want the magnetic field, if it's constant, it's a zero momentum interaction, so you can only see it at the last scale. If like you can see it at any scale you want, but you could sort of defer seeing it as long as you want. And that gives you an explicit formula for the magnetization in terms of the effective actions of the symmetric critical flow that was constructed before. In the slide I showed you, just in terms of that, and with an effective magnetic field that has been scaled up. And now, well, I guess it's getting late. So from this formula, I could now give you a sort of like a two-page heuristics about why the magnetization behaves like this h to the 1/3 with log corrections that I just showed you. And what this has to do, what does this involve? So there's this thing has been constructed by Gawecki-Kupiainen, and I will just take it you can use the result to justify certain approximations of this thing. So you could justify replacing this by a quartic polynomial, local polynomial with some coupling constants, lambda n, which was 1/n, and nu n, which was something like -1/n. And then if you do a translation so if you just look at this is now really sort of the original form. You have e to the minus a magnetic field, which has been scaled up, e to the minus something quartic with new coupling constants. If you translate this integral to the minimum of that action, then you will get an explicit term. I don't do the calculation, but you will get an explicit term which is L to the minus the scale at which you do this operation times the minimizer of this polynomial. And you can justify these kind of translations if there are certain conditions on this minimizer. The minimizer should be large. That will give after you do the translation, it will give you a mass. But it should not be too large so that it messes up your large, what is a large, like your distinction of what a large field and a small field is. And you can so the question is, can you choose your n in such a way that your minimizer, so the scale at which you do the operation, can you choose it so that your minimizer satisfies these two conditions? And yes, you can. And this is the n you have to take. It's something like 1/3 log h inverse, but it's a little bit smaller than that. So you have to subtract something between the 12th log h and the 3rd log h. And you can see that if this is your scale, you can compute this minimizer pretty much exactly, and then you can also compute this first term in the magnetization exactly, and it is h log h inverse time to the 1/3. And so just from sort of using a minimization argument at the right effective scale, you can get the log corrections. You will still have an error term, so the second integral here. Now, how do you treat that? Well, you chose the scale of integration so that this error term has a mass. The mass is quite. You could sort of I just take this mass into my covariance. This gn prime initially did not have a mass. After I do that, it does have a mass. The mass is pretty small. It's like 3 lambda times phi bar squared. Phi bar should be smaller than lambda to the minus a quarter, so this is sort of like square root of lambda at most, this mass. But you can still think of a method that does not use the renormalization group and treats perturbations of Gaussian measure with such a small mass. And these are called, well, I guess I did another step here. These are called cluster expansions with large blocks. Now, these cluster expansions are sort of interpolation formulas between this kind of integral here and the same integral, but where all your integration fields and also the exponential is restricted to fields which lie in a fixed set, a fixed block of that size. So this integral still has many dimensions, like infinitely many in the thermodynamic limit. This is a fixed dimensional integral, and you interpolate between the two, and this interpolation will work under certain conditions. First of all, each of these sort of finite fixed volume activities should be close to 1, and then there should be a bound that that allows you to remove, if you have a certain set, remove one block from that set in the activities. And it will help you. So this kind of approximation will be getting worse and worse the bigger you make your blocks, but this will get better and better the bigger you make your blocks. And in fact, I guess what comes out is that if you make your well, I guess so. Let's talk about this. The second bound, the sort of the bound of removing a block from an activity. You can do that with some kind of Taylor interpolation formula, and the Taylor interpolation formula produces small factors that are coming from these coupling constants lambda and lambda phi bar, and it produces large factors which come from the square root of the covariance. Actually from its L1 norm, but it's not really the L1 norm. If you take a big block, you get something. It's like the L1 norm of the averages, but with a scaling factor L to the minus 2 in front of it, and you pay for this. So L is the size of the blocks. I didn't really mention that. So the bigger you make your blocks, the smaller the contribution to your bounds from the averages of the covariance get, but the contribution from the gradients of the covariance become bigger, but the gradients of these kind of covariance decay much faster anyway than the values themselves. So that's something that's fine. And what you see is that you will get this cluster expansion argument will work as soon as the scale of the cluster expansion. So the minimizer is actually a large field. So if you multiply the minimizer by L, which is the same as multiplying the magnetic field by L cubed, then you should have a large field translation. Then I guess there's some stability aspects involved in proving the second. So that means that you have to take your blocks pretty large. And the question is if you can still prove that. There are some stability issues involved here. So when is the integral of a function like that close to 1? Well, that would better be the case that the things up here are close to 0, but in fact they can be pretty far away from 0 for certain field configurations, and you have to show that the field configurations are unlikely in these kind of measures. So there are some sort of convex functions below all your effective interactions, and you need to show that. And then you can basically prove that the activity of a single block is close to 1 by doing something like zeroth order perturbation theory, writing this as 1 plus that thing minus 1. And I guess I just conclude. So if you want to construct the critical behavior of the magnetization, what you should do, even though it's a non-symmetric problem, you should still follow the symmetric flow that Gawęcki-Koopmanianen, for example, have constructed until a certain scale that depends on the magnetic field. At that scale, you translate your field to the minimum of the effective action, which removes the magnetic field and sort of moves it into an explicit term. That explicit term has the asymptotics that are written here, and the remainder you can control by a single cluster expansion. So you don't need an RG argument anymore. A single cluster expansion which has scale large enough so that your minimizer at that scale becomes a large field. Okay, so that's all I wanted to say. Thank you.
So is there a way in which your scheme could be turned into a practical approximation scheme? Let's say that could appear in a physics book. Physics book, you do Feynman diagrams and perturbation theory, but would there be a way to say here's this additional clusters that you also need to take into account to get a better approximation for it? Can this be turned into some?
So I certainly think that
you do bounds and things like that, so there's clearly something that can be done. I mean, obviously.
Yeah.
There's something. Tell someone who doesn't really want to know all the formalism, what other terms
I think
how it should be set up differently from perturbation.
Yeah, I think it would be worthwhile for people to think instead of perturbation theory like computing, say, first and second order perturbation theory, what they could do is compute these two quantities instead, which include all of first and second order perturbation theory, but they also have stability aspects of the model built in, which are important for the magnetization and that kind of stuff. But I would not try to, well, I mean, it's not like these cluster expansions, for example, or the multi-scale cluster expansions have too terrible of an algebra to work with, but it's certainly worse than perturbation theory, the algebra. And it's always that, always resumming infinitely many terms in the perturbation theory, right? Yeah.
Your RG transformations flow towards the infrared Gaussian fixed point with some logarithmic terms. Can you say how big a domain you can start from in terms of the couplings which flows to this point? Are there any?
Yes. Yeah. So I don't know what kind of perturbations you want to allow. So for the non-symmetric, I only put a magnetic field, right? And I think you would get pretty effective bounds about how big your magnetic field you allow. So I'm interested in the limit that the magnetic field goes to 0, but I could give you exact bounds about like how big is the initial coupling constant, how big can your magnetic field be, so that I get sort of effective error estimates. And the same also for the non-symmetric construction. It's just that nobody ever optimizes them. So it would be just silly to give you a number now.
I mean, your basic side of the fourth coupling is a dimensionless number.
Yeah.
Are you assuming this is small compared with 1, or
Oh yeah.
bigger than 1?
No, much smaller than 1. Yeah, it's not going to be a very effective. I think it will be like 10 to the minus 10 to the 10 or something like that, right? So there's going to be a bunch of exponentials there in the technical conditions. It would be actually, I think it would be useful to understand exactly the radius of convergence of arguments like that, like a little bit more exactly. But yeah, I don't know.
The question I have a question too. So the question I was asking earlier was about the fluctuation field at each scale if it averages spatially, because this is why you don't see the magnetic field until the very end.
Yes.
But then when you see it extremely strong.
That's right. So if you were to do it at the last scale, then.
So is there a way of kind of making it flow by changing the way you?
Yeah, but then you generate this other direction, like the cubic one, and then you have to deal with that thing blowing up, and so. Like it doesn't blow up very fast, so you'll be massive before it blows up. But there's some stability aspect involved there that would be much harder to do if you have if you're sort of working with external fields. Like I never have external fields; I only do one integration, and so my stability aspect is just slightly simpler than that. But what you're suggesting, of course, if you translate your field very early and produce these other relevant terms, then you could treat more general, more sort of generic perturbations.
Because you really have to use the kind of the old layer CNI nested interval to construct your stable map.
I let Govetzky-Kopianin do it, right? And then I just work with their result. I mean, it is a massive theory, right? You're not at a critical point if you have a magnetic field. So in principle, you don't. I guess I could get some like a little bit more general result than I have if you start like you have a magnetization, but you start slightly off the critical surface. I could show you when it stops being a third root and becomes linear again, or something like that. But yeah, it's not very interesting, I guess.
Questions? If not, let's thank our speaker.